Hello everyone and welcome to my channel Maths with Lazy Bee. In this video, we'll be discussing the question which had been asked in Jee Advanced 2024. And this question is from the topic 3D geometry and vectors. The question says that you have gamma, a real number, and you have two lines. And we have been given that the lines intersect and this gamma, we don't know this gamma. So these lines intersect. By looking at these two lines, you have the direction ratios 1, 2, 3, and this is for line 1, and for line 2 you have 3, 2 gamma. So you can see that these are not parallel. These direction ratios are not linearly dependent, because if you try equating one as the constant multiple of the other, you get 3c, and for the other you get 2c. So this means C is 1 by 3, but the other is giving you C equals to 1, which is not possible. C cannot take two values at the same time. So this means that these are not parallel. So these lines are not parallel to each other. We'll be using this thing to find out the normal vector of the plane. Okay, so these lines intersect. So this is the equation of the line 1, and this is the equation of the line 2. So these lines intersect. So how do you write the equation of two lines? So you have this from where the line passes, a point from where the line passes, and the other is the vector to which the line is parallel. So this is the equation of line 1. And similarly, you can find the equation of the line 2, which is, and lambda keeps on varying in R, because for each real number lambda, you will be getting a different point on the line, lying on the line. So this is the line 1, and to find each point lying on the line, you need a different value of lambda. So this is the purpose of lambda. So you are finding the equation of line 2. Although you don't need this, but still I'm writing it. So you don't have gamma right now. So our task will be to evaluate gamma, because we need gamma to solve the part P, and we need R as well. We need the normal vector. And once we have OR1 and n gap, then we can find out OR dot product of OR and n cap. So right now the task is to find gamma and to find the point of intersection. And because of that, we'll be getting OR1 vector. So since these lines intersect, you will be equating them, the x components and the y components. See, this is the line L1 and this is the line L2. These lines intersect at a point. So that means there is a point that is lying both on L1 and L2. So let x, y, z be that point, be the intersection point. This is intersection point I, which is lying on both. That means x, y, z lies on both. Both means that you will be getting a T1 in R such that x, y, z equals to the components given by the line L1. So what are these? Minus 11 plus 2, T1 minus 21 plus 2 T2 and minus 20, this is T1 only, T1 and minus 29 plus 3 T1. Similarly, there is a point T2 in R such that since XYZ is lying on L2 also, so XYZ equals to the components given by the line L2. So minus 16 plus 3T2 minus 11 plus 2T2 and minus 4 plus gamma T2. Okay, because these are equal. See what we did, we had two lines L1 and L2, and these lines intersect at a point XYZ. So we need to find XYZ, and we also need to find this gamma, this gamma. And since XYZ is lying on L1, so that means there is some T1 in R, because to find the points lying on a line, what do? We vary that lambda, that constant lambda. If it is 1, it is 2.2, it will be taking all the real numbers, the values of all the real numbers, and you're getting all the lines, because line is getting infinitely extended. So for all the real numbers, it will be getting points on L1. And similarly, to evaluate the points lying on the line L2, we will be varying mu, because this time the constant is mu. So different mu's give you different points lying on the line L2. Since we have a point that is lying on both the lines, that means we have some T1 for which our components will be this, and these components lie on L1. And since these components lie on L2 as well, so then at that time we'll be using the equation of the line L2. So these are equal, and now we'll be equating them together. Equating them, we get T1 equals to minus 16 plus T2. This gives you 5 equals to 3 T2 minus T1. The other line gives you minus 21 T2 to T2 to T1. This gives you minus 10 equals to 2 minus T1, which gives you T2 minus T1 equals to minus 5. Now notice that you have two equations and you have two unknown variables. Two equations and two variables. That means we can solve these equations and we can evaluate the values of these T2 and T1. Okay, so solving them, because ultimately we need T1 and T2 because we want the intersection point R1. So using the matrix method or elimination method, you can find simply you get T2 equals to 5, and substituting this here, you get T1 equals to 10. So now you have the values of T2 and T1. T1 equals to 10, T2 equals to 5. And now since we have got T1 and T2, we can also get gamma, because we have T1, the Z point of the line L1 gives us minus 29 plus 30, because T1 is 10, so this is 1, and this gives us minus 4 plus gamma into 5. Equating them, we get gamma equals to 1. So gamma is 1. Also, we can find the intersection point. Since we have gamma, we have T1 and T2. So you can use this L1 or L2, anything, your choice, to evaluate X, Y, Z, because that is going to give us the intersection point. So this is minus 16 plus 3 into 10. The next point is going to be minus 11 plus 2 into 10, and minus 11 plus 10. So the point is T2. No, sorry. I'm sorry. T2 is 5 actually. So this is going to give us an incorrect answer. This gives 1, this gives minus 1, and this gives minus 1. Minus 1, minus 1, 1. So this is the intersection point. Now, seeing the answers, minus 1, minus 1, minus 1. Sorry, minus 1, minus 1, 1. So OR1 is this one. This is R. And gamma is 1. So this is P. Okay. So checking the options below, we get that R is 1. So we have these options. And since P is 3, so either this is the answer or this is the answer. Because P is 3 in options A and C. So this or this. Now see that in both of A and C, we have Q. The answer of Q is 4. So Q is 4. Although we will be evaluating, we will see how to find this normal vector. So we just need to figure out what is S to find the final answer. But to find out S also, we need the normal vector. So since you have the n vector, which is the fourth option, you can take the dot product of this with the OR vector, which is given by this. And if you take the dot product, what do you get? You get minus 1 by root 6. You get 2 by root 6 plus 1 by root 6. Oh, sorry, this is plus 2. This is minus, and this is, this gives you 0. Minus I cap minus j cap plus k cap. And the n vector is this. No, sorry. This gives you, this is 3n. So this is 2 by root 6. So this is 2 by root 6. Simplifying it, you get root 2, root 2, root 2, root 3. And you can cancel it over root 2 by root 3. So S is 5. S is 5. That means C. C part is the final answer. So once you got the value of gamma and you got the intersection point R, so you also got the value, the answer for the part Q for free, and using that you could easily find out the option for S. So you got the S, and the final answer is C. But how to actually find out the normal vector? So to find out the normal vector, remember that you have two lines which are lying on the plane. There is a plane and there are two lines, and since the lines are not parallel to each other, so these can be like this or these can be like this, but these are not parallel. So this is line 1, this is line 2, but arrows won't be there because we are not talking about a vector. So this is line 1 and this is line 2. And since these intersect, there is a point, and these are, this is the line 2. Now this is the plane, and L1 is not parallel to L2. So that means any plane, if the plane is not passing through origin, if the plane is passing through origin, then it is fine because it is going to be, plane is two-dimensional, right? Plane is two-dimensional, and we have two vectors. If the plane is passing through origin, then and we have two vectors that are not parallel to each other, then those two vectors can easily determine the normal vector, because you take the cross product and you take the vector You get the vector that is, because a plane is two-dimensional. So you need two linearly independent vectors to determine all the points lying on the plane, because we have, if this is V1 and this is V2, and we take linear combination of these vectors since these are linearly independent. So the V1 and V2 span the entire plane. And if the plane is not passing through the origin, see, here we can write as a linear combination, and if we take where A and B are in R, and if we take both of them to be 0, we'll be getting 0. So this means that the plane is passing through the origin. So it is actually a subspace, or is a vector space. A plane is a vector space only if it is passing through the origin. So it is, you don't even need to remember whether it is a vector space right now, because in 12th you don't know all these things. But it is two-dimensional. So any two vectors which are not pointing in each other's direction or in only one direction, if there are vectors with two vectors which are not pointing in each other's direction or in a single direction, then we can use them to find the normal vector of the plane. So if the plane is passing through origin and we have two vectors lying on the plane, because you have two vectors, different vectors, one in this direction, one in this direction, and you take the cross product, you get the normal vector of the plane, because the cross product gives you the vectors which are perpendicular to both the vectors. Cross product of a vector gives you a vector that is perpendicular to both the vectors. But if the plane is not passing through origin, then you can define a similar plane, a copy of the plane that is actually passing through the origin. And you have the drs of L1, you have the drs of L2, direction ratios. So these are actually free vectors. You can define them anywhere, but the vector is same. You can define them starting from the origin, or you define them anywhere else. So you have these drs, and you can define a plane that is parallel to the plane given to us, say pi, and you take pi naught that is passing through the origin. So you define these vectors. So this is the plane, and these planes are going to be parallel to each other. Because we didn't do anything, we just shifted the plane which was not passing from the origin to a plane. We just made the copy. So the planes are actually parallel to each other. So if we use, and the plane is passing through the origin. So if we use these vectors, which are the direction ratios, and you find the normal vector, which is normal to this plane. And since this plane is parallel to the given plane, so the normal vector of the plane passing through the origin will also be a normal vector for the plane that is given to us. So, cutting the long story short, you just need to find the cross product of the drs of the line. For L1 it is 1, 2, 3, and for L2 it is 3, 2, 1. So to find the cross product, you use i-j+k. So this is 1, this is 2, this is 3, this is 3, 2, 1, and you get 2 minus 6. For this you get 1 minus 9, and for the k component you get 2 minus 6. So you get minus 4 I cap minus plus 8 j cap and minus 4 k cap. So you don't need the scalar multiple, you just need the vector only, because the scalar multiple is just going to be of higher magnitude than the original one, because we are multiplying it with 4. And you can also take the minus out, so you'll be getting minus 4. This is going to be minus 2, and this is going to be just k. This is going to be the normal vector. But if you want a unit vector, then you can divide it by the magnitude, which is going to be root 6. And this was the answer of the Q part, which was 1 minus 2, 1. So this is answer. Q part. So when you have a plane and you have two lines lying on it, which are intersecting, or even if they are not intersecting. So if you have two vectors, because L2 is parallel to some vector whose direction ratios are 1, 2, 3, and L1 is parallel to the vector which is whose direction ratios is 1, 2, 3, and L2 is the line whose direction ratio is 1. So you have two vectors, and these lines are not parallel to each other. So you have two vectors which can determine since these are not linearly dependent, and in 2D, if the vectors are not linearly dependent, see, the plane is two-dimensional, plane is two-dimensional. Plane is a two-dimensional object, and you have two vectors which are linearly independent. So these will be the bases as well, or will be spanning the plane as well. But this happens when plane is two-dimensional, but the plane is passing through the origin. In that case, it is a vector space. And when the plane is not passing through the origin, in that case, you can't talk about basis. You can't talk about spanning, because spanning happens when we are talking about vector space. But when we shift the plane from the origin to a certain point, when we shift the plane, then we are not talking about the basis. But here the point was that we don't know whether the point is passing through the origin or not. And we have two lines which are lying flat on this plane. We have the direction ratio. So this line is parallel to the vector given by 3, 2, 1, and this line is actually parallel to the vector given by 1, 2, 3. Fine. And these are free vectors. These are free vectors. If you are defining them with their starting point at the origin, then also it's fine. If you're taking it somewhere else, then also it is fine, but the vector remains same. You can define it anywhere. So what do we do in this case? We actually make, because we know that if this plane passes through the origin, then it will be then we can talk about the basis. Okay, so this is parallel to a vector d1. We can directly take this 3, 2, 1, and this is going to be 1, 2, 3. Sorry, it was 1, 2, 3, and this was 3, 2, 1. Anyways, this is 1, 2, 3. So we can take the cross product. Now, after taking cross product, you get a vector that is perpendicular to both the vectors d1 and d2. And this plane, which was the original plane, and this is the copy plane, since these are parallel to each other, so if we have a normal vector to this plane, this is also going to serve as the normal vector of the original plane. So that is the reason we take the cross product of these vectors, because cross product is giving a vector that is perpendicular to the plane passing through the origin. And since the copy plane is actually parallel to the original plane, so we can talk about the normal vector of that plane also, because that is going to be the same. So this was all about this question. I hope you understood, but if still you have any queries, please feel free to ask in the comment section. Till then, see you in the next video and happy learning.